Okay, good morning again for the video, and it's again clustering day. If you remember last time we studied k-means. Okay, today we do some exercises with the same k-mean algorithm. So the first exercise is we have some data. In the data, if you remember, we had an exercise where we created some data. The last, which you will find in your book, which is exercise 2.2. Okay, so with the same exercise, with the same data, we will apply now k-mean algorithm. So the data was, just to remind you again, we had two groups of data. The one we generated was something like this. We had a normal distribution, we had number of points were 10. Okay, so it was an n by p matrix. And similarly, the second group of data was n2 by p, n2 was 20, and we shifted the data a bit from the normal distribution. Okay, so each point is shifted by dx equal to 5. Okay, so we use the same data set. Now the task in this exercise is to recalling k-means. The first step in k-means was to initialize with some random points for data. So the exercise is asking to initialize the k-mean clustering with these 3 points: 5, 15, 25. 5, 15, 25 means in your data set, row number 5, row number 15, row number 25. Initialize those points as initial centroids, but we know those are not yet centroids, but our initial random points. So this is the first step. The second step in k-mean was now to calculate the distance of each point towards these initialized points. So the distance from all the points towards these newly initialized points. Okay? And then the next step was to assign these points to the clusters having the minimum distance. Okay? And then we do this step. We repeat step number 2, step number 3 until we converge, and these new centroids are now equal to the mean value of each cluster. Okay? So this way we find the cluster 1, 2, cluster 3. So the question is clear. We have to just apply k-mean algorithm. 3 steps. Initialize with these random numbers. Calculate the distance from each point to these new initialized points. Okay? And then assign these new points to the clusters having the minimum distance. And in the next step, then we recompute this distance between the new centroids and the mean value. If you remember, we were moving. Okay, so our initial points were here. Just a quick reminder. Okay, so we had these points, and we know the mean is here. We started, maybe let's say number 5 is here. So the first thing was to calculate all the distances from each point to here. Okay, and then we choose between all the minimum distance. So the minimum should be the shortest distance. And to calculate this distance, we cannot do this in one step. So we do this step by step. Maybe the first step is this, the second is this, the third is this, the fourth is this. Okay? So we move until this, the mean value is equal to the centroid. and this means we converge. Okay, and then we say, okay, this for me is the cluster I want to be. So we have 5, 15, 25. These are our row numbers, and the clusters are the columns. Okay, so C1, C2, C3. So we have rows and we have our clusters, 3 clusters and n number of rows. So something like this. Okay. Inside the data is organized in a matrix form like this. So we have row number 1 for our data, row number 2, these are rows. And each column represents single cluster. So we have 3 clusters, 5, 15 and 25, okay? So what we do, we calculate the distance from each point to all centroids. So we have 3 centroids. So from each point of our data set to all those centroids. And then the distance of all units to the centroid to find the minimum. Okay, this way we choose. This is just a graphical illustration inside the data set, what we are coding in MATLAB. Okay, so in MATLAB how we can do? We initialize our index. We call it a variable index, which is 5, 15, 25. We want 3 clusters, so k equal to 3. Okay, and this is the initialized centroid. So we extract from our matrix of data, which is x, just those indexes, these 3 indexes. Okay, so this way we initialize these 3 as our first 3 points to initialize from our whole data set. And the next step is to calculate the distances. So for the distances, let's define a new distance matrix. Remember the very first example we did for in the case of where we were choosing the water example. You remember? We had like 5 different types of water and we had a distance matrix. So basically here we are reconstructing that kind of distance matrix. So we initialized it with all zeros. Okay, and then we iterate for the 3 clusters. So if we have k equal to 1, the first cluster, what we calculate? The mean value. So all the distance minus the centroid. So each point minus the centroid, okay, x minus x bar, and then we square them, so the difference of the sum of the square values to find the minimum distance. So x minus these centroids, we square them and we sum them, and then this 2 means to do it on the second dimension. Second dimension was what? The column. So in the column we have clusters. So these two represent the column. Okay. So this is the first step, to calculate all the distances. The second one is to calculate what? The minimum distance from each point to the cluster. Okay? And this can be done with the help of distance and these indexes. So you have a function like this, distance and index, and it takes 3 values to find what? To find the minimum distance, and where actually that minimum distance is, its index. Okay, so minimum d is we found here in the first step. Okay, and 2 again is the second column. So here we will have the minimum distance. Okay, so this means that if we have a unit I, which cluster is assigned based on this minimum distance. Okay, so if we have, let's say, index 2 equal to cluster number 3. Okay, so point 2 in your data set, any point, let's say point number 2 is having a minimum distance between cluster 3. For instance, another example, we have another point which is point number 15, and point number 15 has a minimum distance to cluster number 1. So we say point 15, we assign point 15 to cluster number 1. Okay? So the basic idea here is this, to find the minimum distance, the index, and then assign it to the cluster. Okay, this is a list where we register now these values. 2 is the column. So the column is our clusters, and the row is our data. So we select like the second dimension. Okay, look, these are our columns. Okay, we sum these distances. We choose the minimum between in any column. Cluster 1, cluster 2, cluster 3. Minimum distance here, minimum here, minimum here. So we will have 3 distances. Okay, and then we choose the minimum between those 3s. Are you with me? You have to imagine something sometimes. Now the third step is to update the centroid. So now we move. Okay? By using this formula now. So first, we are working inside the cluster. So inside the cluster, we found this distance from each point to its mean. We square them, we sum them. Okay? And now to update the centroid, we sum them with respect to all the other clusters. So first within each cluster, this is within each cluster, and then on the whole data, compare with all the clusters. Okay? And this can be done this way. So for example, from our data, we say index. If any point whose cluster is equal to j, for any point, if the cluster is equal to j, and we calculate this mean distance for that point, so we say the index of that centroid is equal to the mean. Okay? Are you with me? So this way, meaning if we have an index I is equal to, let's say we have a point 2 and cluster number 1. Okay? So this way we collect all the points, those are inside cluster J. We collect all the points from our data set that belongs to cluster J. Okay? Then we check if the centroid of this cluster is equal to the mean of this cluster. Okay? If this is the case, we are in the same cluster. Then we perform this, we apply this formula. Are we sleeping or? Okay. And we repeat this. We repeat this until we converge. When we calculate this, after first iteration, we get the value which is 67.65. So performing these 3 steps. Okay? Step number 1, initializing the data. Step number 2, calculating the minimum distance from each point to the centroid. And then finally assigning each point to its specific cluster. We obtain this value. Okay, just after 1 iteration. Keep this value in mind. We will come to it later. Okay. Now, so that result was just for 1 single iteration. Now we want to do the same algorithm, but repeat step number 2 and step number 3 10 times. Okay, so each time we are coming close to the mean. If we take one iteration, we recalculate the distance. If we take another step, we recalculate the distance. Okay, it's the same algorithm, but just we want to do it, repeat step number 2, step number 3 10 times.
What about the sum? Where's sum?
Which sum?
67 at the end of your sum.
This value?
Just go back.
Yeah.
Sum.
This one?
Yeah.
This one basically counts. We initialized it equal to 0. So each time we have a value here, we just sum them and finally we get this value.
Which represents?
Which is, we will come to this. I said keep this somewhere in your memory. Okay? It's just a number showing you your clusters are doing well or not. I will come to this. Okay, so now we want to repeat it 10 times. Okay, when we start repeating it, so we are coming towards the mean. Okay, so each time we are coming towards the mean, the distance becoming minimum, 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 we are reducing the error. Okay, so at some point we stabilize. And remember we said from the last lecture that we are coming here, but at some point then this point oscillate. Okay, am I a truck or am I a car? Okay, so this distance is decreasing, and at a certain point then we have to decide. Okay, and that for us is a convergence point. So this curve each time, so let's say this is the distance. So this is first iteration. Okay, the distance is decreasing. So first iteration number 1, we are here. Iteration number 1, we are going towards our mean. Then we have iteration number 2nd. So this is 2nd. Okay, we are going close. So remember, this curve will always goes on decreasing, not goes on increasing, because the distance we are reducing it. So at a certain point, then this distance will no more be decreasing. Okay, so when we reach here, there is no more decreasing of this distance. Okay.
Because if saying how many iteration we should, maybe it's not getting in the 10 iteration.
Sorry.
It's not reached to. For example, how many iteration we should try, because sometimes after doing 10 iteration, it's not reaching to the mean
Yeah.
of the center.
So, yeah.
I
Yeah.
think when we have no change, when it's stable,
Yes.
without stuff.
It's clear.
I understand. It is very satisfying.
It's very simple. It's very simple. It's very simple. When you are eating, when you start eating, you're eating more. Then a certain point, maybe the dish is very delicious. From here you want to eat more, but from here it's not going inside. So you say stop. Okay? But we will know about this. We have a specific function in MATLAB which can choose for you the optimal k. We are going to that. Okay? So now we do 10 iterations. Very simple. We just define k now. We have the same data. We have the same initialized 3 points. Now k is equal to this. Okay? And how much is the size of our data? We take that into consideration. We initialize again as the previous example, the initial centroids, the distance matrix, but now we use iterations equal to 10. Okay? Look, this example is in your book 2.8. So here we have to use 2 for loops. Okay? One for the outer summation, one for the inner summation. Okay? And we repeat the outer summation like 10 times. But as we noticed here, you will get a graph like this. So we did not need it to go until 10 iteration. But at iteration number 3, it became flat. Okay, it converges. So there is no more decrease or no more increase. Increase is out of question, but there is no more decrease. So you have a saturation point. When you see this saturation point, you decide, okay, this much iteration is enough for me. Okay? Because if you go beyond this, there is no further improvement. This distance between the mean of a cluster and the distance between the point, there is no more decrease. Even if you are going 10 million times, there is no more improvement. So you say, okay, I stop here. Okay, the same thing, the same 2 examples, we wrote like manual coding. Okay, we code each step. For the k-means, step number 1, we did manual coding. Step number 2, we coded everything. Step number 3, we did hard coding. But in MATLAB, you can do the same thing just with this function. Okay, and the function is k-means. It requires these 4 arguments. Number first is your data set. Okay, your matrix, which is X. Then how many clusters you want? 3, 2, 4. Okay, and then replicates. Replicates is interesting here, because if last lecture we also said it depends on these initial points in step number 1. Okay, each time we do a new experiment to find the optimal value of k. It depends on the initial values, on the initial points. Okay, so each time we will have a different result, slight different result. So this means the end clustering, the end distance, this distance to reach the convergence point depends on these initial points, how you choose them. So each time, for instance, you have chosen here, maybe you get a graph like this. Next time you chose this point here, and now you're coming this way. Maybe this distance now is this. Okay? So there is a slight change between 2 different random initialization. Okay, and that's what replicates do. So replicates repeat the same experiment with 10 different, in this case, with 10 different initialized points. So in the first run, it choose 1 initial point, and it do all the 3 steps of k-means. And it repeat the same experiment with a different initialized point, repeat all the 3 steps until it tries all the 10 different multiple starting points. Okay? Now in this another example, which is exercise 2.6, the goal is to choose k equal to 3 and use replicate equal to 100. Okay, and we should display this, the scatter plot, show the centroid points, and the minimum value of the objective function, the last objective function, which is step number 3. Okay, so the exercise is clear. We have to divide our data set in 3 clusters. But doing this, we have to use the MATLAB function k-means with the option of replicate, and replicate is equal to 100, meaning that this 3 steps of k will repeat 100 times.
Don't we have like something similar to replicate how the number of clusters?
The number of clusters, the optimal number of clusters, yes, we have something that's coming next. Okay, so we repeat it 100 times and we choose the best one. Okay, so repeating it 100 times we will have 100 different values of k, and then we choose the best one where we have the minimum of the distance. Okay, and this example we do in MATLAB like this. So we have the indexes, which was in the previous example as those 3 points. Okay, then we have the centroids and the sum of the final objective function, which will be equal to using the function of the MATLAB, which is k-means, our data. We want 3 clusters, replicate equal to 100. Okay, now to show these centroids, those initial 3 points on the graph, our second step for that was to see the mean value, if the mean value is equal to the value of the centroid or not. Okay, so centroid equal to GRP stats, this calculates the mean value of the cluster. Okay, this function calculate the mean value of the cluster. So we check if this is equal to, so this value would be equal to centroid. And then we put like for a sanity check, we put as this function, and we see if the absolute value of the difference between the actual value and minus the value we calculated here, if this difference is less than or equal to this, so it shows to us just error. Okay, so this is just for sanity check, if we reach the centroid is equal to the mean value or not. And then just is a matter of plotting. Okay, so remember before this value was 67. Okay, now it's changed. So what it does, this replicate, it minimizes this value, but the other important thing is usually if we choose like just a single k, maybe we don't reach to a global minimum. Okay, when we have a function, okay, it's somewhere, but we are not sure it's 100%. In the next experiment, our value will be close to it or not. Okay, so if we use replicate and we use many more iterations, then we are sure that probably this value will be very near to the value of the minimized objective function will be very close to here. So in the previous case, it could be very misleading. Okay, we could have different clusters. Maybe some of the data of one cluster could have been overlapped with the other cluster, but this way we are sure. Okay, and if you plot them, you see we have these 3 groups. So this is the black one, the blue one, and the red one. And if you carefully see these stars are our centroids. Okay, the mean values. So also from here you can get the idea. So the first group is 5.2, 5.1. Okay. So 5.2, 5.1. We are here. And even from here you can guess that it's the most higher value. So it's the upper top in your cluster. So this is the cluster at the top right. Okay. Then we have the other one, this one, and the other one. Okay. So this is this one, the second one. But keep also remember this point, that these clusters, k-means does not show to us these output values in order. So if you see minus 2.7, it should be this cluster. So if we are starting from here, cluster 1, cluster 2, cluster 3, okay, it should show us this, then this, and then this should be the third one. But k-mean don't know about these values, so it gives you the random output. Okay, that's then up to us to figure out which values are where in the plot. Okay. Okay. Now, choosing the optimal number of clusters. If one can see to a data and it say, okay, are doing the non-hierarchical clustering, how can we choose? 2 clusters are enough, 3 are enough, 4 are enough. We don't have any idea. So how we can have the answer for the optimal cluster? What should be the optimal value of k for a given data set? So the natural solution to it comes to mind is, let's repeat with as much k, as many k as possible. Okay. So we start with n number of clusters, then we say n minus 1, n minus 2, n minus 3, and we go like this. And then we compare all the clusters and we choose this cluster is the best one. Choosing the best cluster depends on 2 factors. Okay? We all should know this now. To look for the optimality of cluster, we see 2 things. Within cluster, the variance, yeah? Brilliant. And 2 clusters should be far apart from. So in the first attempt, we try to do experiment with as many k's as possible, and then we choose the best based on these 2 criteria. Okay? But to choose the optimal one, in MATLAB, we have this function. It can give you the optimal one, how many clusters to choose. So you have a data set in front of you. You don't know how many clusters to choose. Okay? So we have this function. Let me try to pronounce it. Kalensky-Harabanov. Okay. I don't know if it's Greek or okay. No, it's Kalensky-Harabas. Okay. So to find the optimal value of k, we use this function eval clusters, and this gives us the optimal number of clusters, the value of k. This function requires 3 inputs. The first one is the original data, your matrix X. The second is the clustering algorithm, which algorithm we want to use, k-means or other type of algorithms. The third one is this criteria, which is Kalensky-Harabas. Okay, and this is the criteria to tell you if this number of k is optimal or not. Okay? So when we are using this function, evolve cluster, it also accepts another argument, a fourth argument, which is with how many clusters you want to start. Okay? So normally, the default value, it starts from 1 to 5 clusters. But you can also choose. Say, okay, I want 10 clusters. Let's try 10 clusters and tell me which one are 4 clusters optimal, 5 optimal, or 9 optimal. Okay? But in default, if you don't give this information to a range of clusters, by default it chooses 1 to 5 clusters. Okay? And it checks between those 5 clusters based on this criteria which one is the good one. Which number of clusters are good one? 1, 2, 3, 4, 5. Okay? And it's a ratio which is this one. So sum of the errors between the clusters divide by within the clusters. So the sum of square distance between the clusters divide by within the clusters multiply by some ratio, where n is the total number of units in your data set, k is the number, yes? K is the number of clusters, okay? So this is basically a normalization factor. So it the same way we did in regression to penalize the data maybe which is very far from, okay? So kind of provide to it a baseline. So this ratio tells us how to choose the k that maximize this value, okay? And these two by definitions are these. So between the clusters, between two clusters, and within cluster. So sum of the square of the sum of the difference of the square of the distance between them. So if this value is larger, this means we will have a higher value of this, okay? And this value should be smaller to have a good optimal value of k. Okay, something like this. So small within cluster, this distance should be small, and between cluster, this should be large. Okay. So in this way, we will have good clusters. So if this value is higher, we will have good clusters based on those two criteria. Good cluster means what? Within cluster, the variance is small. Between clusters, they are very far from each other. Okay? So, if k is too small, if clusters are very small, if you have less number of clusters, this means that individual cluster is too broad. Okay? So if we have this data, if we have random data and we choose clusters k equal to 2, okay, k equal to 2, maybe we have just these two clusters. Two clusters meaning that this cluster is wide, this cluster is wide. So small number of clusters meaning within clusters the variance will be big. But instead, if we choose k equal to 4, okay, so let's say we have this now and this now. So between the cluster now we have the variance has reduced compared to the previous one, okay? So now we are compact, we shrink. So we choose what? K K, which gives us the maximum value of this ratio. Okay, so meaning that we will have a compact cluster, and between clusters we will have a large difference. In MATLAB we do Kalinski-Hurabus distance like this. This function is evolve clusters. You have your distance matrix, which is X, which algorithm you want to use, k-means, and this guy, and then you should give the another option, which is the range of the k. So how many k's you want to try. In this case you say, okay, from 2 clusters to 10 clusters try, and then give me the optimal k. Okay, so E dot optimal k, and this gives you the optimal number of
Can we just plot,
clusters.
can we just plot the entire thing, make a graph?
Yes, we can. That's your homework. Okay. Exercise now. Choose the optimal number of clusters. So again, the task is to use this function to find the optimal number of clusters and use the range of clusters from 1 to 6. Okay. So this way we will have optimal number of clusters, and then we display the classification. Are you happy now? Okay. So this is your homework. Okay, again the same thing. We use the function evolve cluster, our data, the means, this guy, and now we try 1 to 6 clusters. Okay, then we plot them, scatter plot, then we choose the best index, which one is the optimal one, and the best k value. Then we plot if the centroid is equal to the mean value, and we do this plot. Now if you see number of clusters equal to 2 gives you the higher value of this beloved guy. Okay, so this means in this data set 2 clusters are the optimal one. Okay, and again the same thing. Okay, you can visualize it like this. So how many clusters we have here now? Are we sure there are 2? Okay, we are still alive. So from here you can see, okay, this cluster, this cluster. So between the 2 clusters we have a very good separation, and within clusters they are close. So we should thank this guy. Okay, just this is for the exam or general comments to make. So how we comment? Yes.
What happens if you have outliers on this?
Where? K-means go crazy with outliers.
Yeah, this is what we have.
Problem. That's what we will do if we can reach today or next lecture. You will know how to deal with those outliers. Okay. So for example, if for instance, if we have an example, it says like, suppose we have 2 variables, income and consumptions of 30 consumers. And we have 2 clusters now in this case. So a cluster with centroid, if the centroid is below the overall mean of your data, okay, so we have our whole data. If the centroid is below the mean value of our data, we say that it corresponds to consumers with low income and high consumption. Okay, and similarly the other way around, for if the mean value is higher than the centroid. Yes.
Is it possible, for example, if we choose 1 to 6 clusters, for example, for the 2 we get our value.
Yes.
Like we have that pattern. Is it possible, for example, I choose the range 1 to 15? Maybe right now it's giving the value 2, but after choosing 15, maybe it will be give more values on more higher values on 8 or 9 clusters.
I think then it will depends on the data. So, if in this case, where I'm going, if in this case, okay, you have 2, those are the best one. There are so many factors, but even if you go more K, it becoming worse.
Notice, for example, whenever the cluster is increasing, this will go
Yeah, you're degrading your performance. So going with more cluster doesn't make sense. Even 3,
once we get the higher performance or any cluster, after that it will be go,
yes,
go down.
it will go down. Yeah, for sure. Okay, we have 5 minutes break and then we continue. Sì.
Nel grafico quello che abbiamo visto appena prima, l'ultimo che abbiamo visto, no, non in questo, quello del valore dell'index di Kalinsky, questo, ok? Cioè noi perché scegliamo su 3 non va più basso, perché non scegliamo 3 nel gas?
Sì, perché questo valore, andiamo a vedere questo, se questo ratio ti
Ok,
dà il valore più, okay, we choose K that maximize this value.
Ah, quindi è
So
come-
this is the ratio between cluster and within cluster.
quindi se metto K uguale 3 non è massimizzato,
No, rispetto a 2 avrai un valore minimo.
ok?
So, quindi noi scegliamo l'optimal K basato su questa formula. Se questo valore è il massimo, scegliamo quello. So, per 2 abbiamo questo e per 3 abbiamo questo. Quindi
Ok, allora leggevo proprio male il
meno.
grafico, ok, leggevo proprio male il grafico, ok, capito.
Ok? जी कौन सा वाला ये ओके
जब हमने मीन नहीं निकाला, मिनिमम निकाला,
ये वाला
नहीं, जब मिनिमम का फंक्शन यूज किया था
और
स्टार्टिंग में तो जब पॉइंट्स लगाया था उसका मिनिमम इस जो फंक्शन
यहाँ
ये जो हम ऐसा कर रहे हैं कि पहले हम रैंडम 3 पॉइंट हमने फेंक दिए कहीं पर, हमने उसके डिस्टेंसेस कैलकुलेट करे और उसके बाद मिनिमम हमने उसके निकाल लिए। अब मिनिमम हम उसके लिस्ट में स्टोर कर रहे हैं कहीं पे।
हाँ
अब एक सेंट्रोइड से जैसे मिनिमम निकला, फिर दूसरे से निकला, फिर तीसरे से निकला, फिर उनमें से एक को चूज
फिर उनमें से
एक को
एक
चूज
इस तरह कि ये यहाँ आपके साथ में हो गया, ये आपका पूरा डेटा हो गया, आपको each row हो गया, ये आपका एक क्लस्टर है, ये दूसरा क्लस्टर है, ये दूसरा क्लस्टर है। सो फर्स्ट करें वो देखो इसके हिसाब से हर एक के साथ आप डिस्टेंस सम करते हैं फिर उसको चूज करते हैं।
डेटा के साइज पे भी डिपेंड करता है। एक वजह हो सकती है कि हमें कितना साइज लेना चाहिए, या कितने साइज पे कितने क्लस्टर होते हैं, या फिर ये रैंडम प्रोसेस है जिसके अंदर हम
कंप्लीटली रैंडम है। के मीन्स
Initial बात
हाँ,
है।
क्योंकि हमें पता नहीं है लेवल्स का, स्टिल हम उधर है अनसुपरवाइज्ड
ये
लर्निंग।
अब जैसे हम कहते हैं कि 10 अल्ट्रेशन में हमारी पीक आ जाएगी, हम स्टैग्नेट हो जाएंगे, बट पॉसिबल हो सकता है कि 10 अल्ट्रेशन के अंदर हम समझ रहे हो कि ये हमारा पॉइंट है, लेकिन 15 में है, वो 20 में है, वो 50 में है, 100 में है, फिर हम कितने वैल्यूज हिट रेट ट्रायल में लगाएंगे।
हाँ बिल्कुल, अच्छा क्वेश्चन है ये। तो इसीलिए आप ये इस ग्राफ को हर दफ़ा प्लॉट करोगे। फ़र्ज़ करें आपने 10 आइट्रेशन कर ली और 10 आइट्रेशन में आपका ग्राफ जो है वो नीचे आ रहा है। 10 आइट्रेशन आपके ख़त्म हो गए, लेकिन आपको सेचुरेशन नहीं मिला, तो फिर आप के की वैल्यू को नेक्स्ट ज़्यादा करें। फ़र्ज़ करें आपने 15 कर दिया, तो आप नीचे आए 13 पे या इस तरह पे।
ऑप्टिमल सोल्यूशन ये है कि हिट एंड ट्राई के अलावा जैसे कोई तरीका हो कि जिसमें अल्ट्रेशन मिल जाए डायरेक्ट कि भाई इतनी करनी
वो है, अभी आगे हम जाएंगे, वो मिक्सचर मॉडल्स पे है, वहाँ आप क्या अभी आ जाएंगे। यस,
ये जो आपने बोला कि यहाँ जो आपने ये बताया ये तो नहीं समझ में पा
कौन
समझ
सी
आया। ये जो है ना आपने बोला कि जब ये क्लस्टर उसका आधा आधा कर रहे हैं,
ठीक है, फ़र्ज़ करें जो आपका डेटा, ठीक है, उसमें आप चाहते हैं कि द मेन आइडिया क्या है तुम्हारा, दो कंडीशंस हैं। एक क्लस्टर जो है वो आपका इस तरह होना चाहिए, क्लोज होना चाहिए, तो एक पॉइंट और दूसरे पॉइंट के दरमियान डिस्टेंस कम होना चाहिए। तो मतलब ये है कि ये पॉइंट्स एक दूसरे को सिमिलर हैं। फर्स्ट करें आपके पास एक डेटा, आप कर रहे हैं मेन को, इन दोनों को आप क्लासिफाई करते हैं क्लस्टर पर। तो अगर ये डेटा जितना ज़्यादा नज़दीक होगा, फ़र्ज़ करें मैंगो है, तो इनको ज़्यादा नज़दीक होना चाहिए कि वो सिर्फ मैंगो
समझ गया। अब ये चाहिए ना कि इसको अपन 2% डिवाइड करें, इसको फिर 4 में मतलब इसको 4
तो फ़र्ज़ करें इसी होल डेटा में अगर क्लस्टर आपके पास 2 है, तो हो सकता है कि फ़र्ज़ करें ये थोड़े बड़े हों,
हाँ
मतलब शायद इसमें मैंगो में एप्पल भी अंडर हुआ
हाँ
हो।
मतलब
हाँ, तो मतलब क्लस्टर आपका बड़ा है, एक पॉइंट यहाँ होगा, दूसरा यहाँ होगा, तीसरा यहाँ होगा, चौथा। जब क्लस्टर्स कम होंगे तो पॉइंट्स के बीच डिस्टेंस ज़्यादा, मतलब एक दूसरे से बिल्कुल। अब अगर आप क्लस्टर ज़्यादा करें, 2 की बजाय 4 करें, तो हर क्लस्टर की वैल्यू 2 की वैल्यू निकल जाएगी। तो कॉम्पैक्ट
मतलब आप उसको कंजेस्टेड कर रहे हैं
हाँ,
तो उसको
ताकि, और कंजस्टेड क्यों करते हैं, क्योंकि हम चाह रहे हैं कि जो सिमिलर पॉइंट्स हैं वो एक दूसरे के नज़दीक आए, जितना ज़्यादा नज़दीक वो आ सकते हैं
और भी जो आपने बोला कि जब मीन है वो सेंट्रोइड की इक्वल हो जाए, तब इटरेशन तो हम तब तक कर सकते हैं जब पहले आपने बचाया 5, 10, 25 का मीन निकालेंगे, 15 फॉर एग्जाम्पल आया, तो हमारा जो मीन सेंट्रोइड मतलब मीन सेंट्रोइड 15 तक इटरेशन करेंगे, फिर मीन तक आ जाएंगे, तब तक करें, इससे पूरा ना।
हाँ, तो वहाँ पे फिर ये होगा कि फ़र्ज़ करें आप यहाँ पे पहुँच गए, तो यहाँ से,
मतलब यहाँ मीन की वैल्यू 15 है फॉर एग्जाम्पल।
हाँ, तो यहाँ पे आप स्टॉप करेंगे, क्योंकि इससे ज़्यादा अगर आप जाओगे तो वो डिस्टेंस, ये वाला डिस्टेंस और कम नहीं होता।
बिल्कुल ठीक है, अगर मीन अब इटरेशन तब तक करेंगे जब तक मीन तक वो वैल्यू आ जाए,
हाँ, बस इसका मतलब ये है कि आपके पास अब जो क्लस्टर है वो k = 2 है, वो कॉम्पैक्ट है, सही है। जितना नज़दीक आ गए आप इस केस में आ गए, अगर आप यहाँ पे हैं तो मतलब ये है कि आप इस केस
मैं
में
समझ गया।
Okay, so now let's suppose that we have a data set, we have n units of our data set, okay? So we have a random data set and we used maybe two different kind of algorithms to find the clusters or to find the partitions, okay? So the data set is the same. Data set is the same, but we use two different kind of algorithms to find the clusters. So now what we are interested in to find which algorithm performs better and gives us the good partition, or what is the difference between the resultant partition resulted by these two different algorithms. Okay? So how we can compare two different algorithms with the same data if they results in two different types of clustering. Okay? Yes. So the typical way is to metrics for what?
To evaluate.
Yes. We can use metrics for what? Sorry.
Evaluate the performance of the model.
Yeah, that's where we are going
Oh.
with this. So we compare different partitions. For example, we are using k-mean, but we want to use single linkage distances. We want to use k-mean, but Euclidean distance. Okay, we want to use k-mean, but a complete linkage distance between the points. Okay, so with one type of distance, we will have one type of clustering. With another type of distance, we will have another type of clustering. Okay, so we compare these two methods. Similarly, we can compare between two different type of clustering techniques. Okay, or we use different types of variables. Okay, we use k equal to 5, k equal to 10, the variables are changed, and then we compare results between the two. Or maybe if we have labels, we compare the resultant clusters with the label data. Okay? So for instance, we are in this case where we use two different algorithms, and in the first algorithm we have cluster 1, cluster 2, but on the same data we used another algorithm in which resulted in this kind of overlay. Okay, so this is partition C with method A, same data, partition C star with method number 2. So we are interested to know how similar these two partitions are based on our using two different methods for clustering. Okay, and we can find this comparison between two different methods of partition this way. This is to know, so n divided by 2 means that we have n elements. For instance, n equal to 2 and n equal to 10 and 2. So how many possibilities we have to choose 2 points out of 10? Okay, we have total number of 10 units, and each time we want to pick 2 units from out of these 10. So how many possibilities we have? So we use this formula, right? Okay, so maybe for the first time, unit 1, 3 is one pair, unit 1, 5 is second pair, unit 1, 7 is third pair. So we do this permutation, right? And we ask this question, whether a pair ij belongs to this cluster in method number 1. If yes, so we say yes, it belongs to this cluster. But in the same method, the same data set, different method, we have this cluster. So for the same pair ij, we check these two conditions. If it belongs to this cluster, we say yes. Then we check in this cluster. If the same pair ij also belongs to this cluster, meaning that they are belonging to the same clusters using different methods. Are you with me? Pair ij, unit, let's say row number 2. In row number 2 we have 2 points. Okay, we have this data. Okay, here we have 2 points, point I, unit j. We use 2 methods of clustering, method A, method B. Okay, now we check in this method if those 2, so method A produced these 2 clusters. Okay, method A produced these 2 clusters out of this data. Now we want to check point I and j, if this point I and j belongs to here. So we confirm I, j, method A, we have yes. Those 2 guys are here. Now we use a different method, which is B, and it divided the cluster this way. Now we check again if those 2 points I and j belongs to this cluster or this cluster. If they belong to this cluster, we say yes, and we conclude that the 2 methods are in agreement with each other. So they clusters the points in the same manner. Okay? So both methods divide the data in a similar fashion. Okay? And then we draw a matrix like this, which is C is method 1, C star is method 2, 1 here belongs to, if both the points I and j belongs to the same cluster, we say 1. So for example, for instance, a point C11 belongs to this method and this method, we say 1. They both are in strong agreement. If C10 is where method C says, okay, it's my guy, come to my cluster, but C star say no, let's go with me. Okay, so they are in disagreement. Yes. Similarly, this case, C say no, let's go with me. C star say no, go with me. Okay. So looking to the diagonal C11 and C00, C11, both methods say 1, 1. You are with me. Method 1 say you are my part. Method B say you are my part. Both are in agreement. Let's go together.
It's like the two partition puts the units inside
The same cluster.
the cluster.
Yes. If we look to on contrary C00, okay, I am method A, he is method B. Okay, these new points coming. He said to this new point, you are not with me, go away. Okay, so he's not part of him. Similarly, if the same point then tries to approach to me, I say to him, no, you are not my part. So now we both are in disagreement about the same point. So again the same conclusion. Either we both are in agreement or we both are in disagreement about the same point. It's clear?
So it's like the opposite of C11.
Yes. So 1 means they have the same cluster, 0 means they will have different clusters then. Okay, the same definition. Okay. So for this to know the comparison, how close these two clusters are, we calculate this, and this is by definition, the definition is this, and this method is called RAND index. So we add the two clusters, the two methods where they are fully in agreement plus fully in disagreement, divided by the total number of pairs we can make from n units. Okay, so number of pairs on which partitions are agree, divided by the total number of pairs in our data set. We get something like this. Okay, so agreement, disagreement. If this value is between 0 and 1, so if the value is 0, meaning two clusters do not agree. Okay, if the value is 1, two clusters are identical. Okay, based on this formula. Okay, and then here we need a kind of correction, because sometimes even if both the values are equal to, if the resultant value from here is equal to 0, if this value is equal to 0, meaning that the two clusters do not agree with each other. If they don't agree with each other, we should get 0 value. But in practical scenarios, we don't get 0. Okay, because maybe there is some outlier which is going to the other data set. So we do some kind of adjustment for that, and the adjustment is like this. We create a baseline, and that baseline is that value of R, RAND index minus the expectation of that value divided by the maximum minus the expectation of that value. So you get a baseline. Okay, so this is then a baseline for you.
But so is it like a kind of similarity index between different partitions?
Exactly. And then we call this adjust RAND index. Okay. And then you can see the two conditions, 0 and 1, if they are there. So we have finally 3 conditions here based on this new formula, new adjustment. adjusted random index ARI, we can have three possibilities. This value can have positive value, which means better than the random, but they are in fully agreement, so there is no chance of disagreement. If they are 0, if this value is 0, this means their random level of agreement. If this value is negative, this means that they are worse than random agreement. So random agreement here is what? Is this formula before, so is this one. So this is for us is the baseline. Okay, so this value can be positive. Positive means they are strongly in agreement. If this value is negative, strong in disagreement, kind of. Okay, so you can have these three scenarios.
And so usually what we do is to compare the rank index with the adjusted baseline, the adjusted rank index.
But usually it's preferred to use this method, because here you have adjusted for the by chance error. Okay, and the same thing you can do in FSDA toolbox. You can use a function rand index fs. Okay. Okay. So where you put this for every partition, you put a new label C, and this MATLAB FSDA can give you this value. Okay, if it's close to 1, to 0, or negative. Okay, it's clear? Okay, now we change completely and we say we introduce a new class of clustering. Okay, are we sleeping again? We have 30 minutes. I switch here. Okay, can you listen from here? Now? No? With this? No? Okay. Okay, so we switch now to a new and very important, and which is open to research. Okay, if someone is interested, I don't know, doing your PhD or further studies, this is a very interesting field. Okay, and this is model-based clustering. So what's the idea here? The idea here is, say we have random points. We have a data set where we have time and study. And we want to know the relationship between these two. How much time we spend on study. So kind of relation between them. If you remember in K-mean, what we are doing, simply we want to do this kind of partition. Simple. Okay? We divide the data, in this case, for instance, K equal to 3, and we have 3 partitions. Okay? But now we are changing gears to model-based clustering. So the idea here is, if we have the same points, I hope one can draw them the same, but we are not perfect, right? Okay. So the idea here is, we may have clusters like this. here is no clear partition in model-based clustering. With the k-mean, we have a clear partition. Okay, we kind of one cluster this, and this. But in the model-based, we don't have. Because in nature, if we take this cluster, for instance, the top one, and we slice it like this, we never get a clear boundaries like this in reality. Okay? So this is cluster. We are out here, we go inside, and we out. This is a clear boundary, this is a clear boundary. We never get something like this in reality. Okay, is it true? But instead, in reality, we get something else, which is we have a kind of distribution. Okay? So this data is like this if we assume that cluster is normally distributed or it has a Gaussian distribution. So we can never get a clear boundaries like this, but usually we can have something like this. Okay, is it clear till now? So something inside here is clear to us, and on the tails we have a kind of fuzzy distribution. Okay? So that's the reason if here we have this overlap between them. With these models, with these model-based clustering, we can define this region. The overlap, the intersection. But here in this case, we cannot sense that. Okay? Now, so usually to find these places, this overlap region, this fuzzy region, which is here in the tails, okay, we find these regions with the help of probabilities. So we say these points here, how much probable, for instance, we have a point here x1, and how much probability we have that this point x1 belongs to cluster 1, cluster 2, or cluster 3. So we find this probability, and the maximum probability, if it has for this cluster or for this cluster or for this cluster, we assign it to that cluster. Okay? Okay. So, we have something like this. Based on now this new thing came into picture, which is probability. So, we have this. And what's wrong with you? Okay. Can you see it? It's
No,
no.
it's invisible.
try another one. Okay. So the idea in model-based clustering is that each point here, each point in our data set has some distribution. Okay? So we can divide this data into subgroups, small groups, and we say each of those groups then follow some kind of distribution. Okay? So this may follow distribution like this may follow distribution like this may follow distribution like this. Okay? So, maybe we have something like this. Okay, so these are our mean values here. Okay, So we have 3 points, maybe in this region. In this region, we have 3 points. And those 3 points has this kind of distribution. So what we say now, based on the probability to associate them to those 3 clusters, if we see, let's say, okay, the probability here for cluster number 1, let's say cluster number 1 is this one, this probability is higher. So one is probability, the next thing is its density. Okay, higher density, higher probability, we say this point belong to this cluster. Okay, in this case it has a very less probability for this point to be here, so we don't consider this point to be in this cluster. But if we see here, this has a bit more probability than this, which is this cluster. So we say, okay, we have to decide between these 2 clusters, between these 2 distributions, and between them the maximum is this one. So we assign this point to this cluster. Is it clear? So now we are shifting from okay, this is kind of hard classification. So you are sure 100% and you say, okay, this is one thing, this is another thing, and this is another thing. Finished here. But here you also discover these points. Discovering these points depends on 2 things. How much probability we have for this point to be in this cluster, or this point to be in this cluster, or this point to be in this cluster. The maximum of probability for this point for any of the cluster, we say, okay, it's belong to this instance in this case. Okay, and then there are so many other things which comes into the picture, which is like, when we calculate the variance of this, the variance is big or small. What about the mean value? Okay. This was just a general idea. The shift from here to here is this shift. Okay. We consider 2 things here: the density and the probability to distinguish or to classify or to make clusters between our points. Okay. And it takes this form, where phi g is the probability and f g of x is is the density. Okay, the density of that distribution, and this is the number of times, the probability, the proportion. Okay. So hard coding, hard classification before was like hard classification. We draw the line, okay, this is cluster 1, this is cluster 2, this is cluster 3. But now we are shifting to soft classification. In this soft classification, we take even these points, okay, those which are overlapping. Before we do we remember the point when we said, okay, there is a point where we have to oscillate. We have to jump to this cluster or to this cluster. We remember this point, right? This is exactly here. We were not able to make the 200% prediction there, that this oscillating point belongs to this cluster or to this cluster. Okay, we don't have any criteria in this case, but now we have.
It's like you said the last lessons when, like the point, we had to flip a coin. To know.
Yes, we have to
Now
flip a
we
coin.
can.
Yeah, okay. The intuition is clear. Okay. Okay. Now choosing the number, how much time we have? Oh, we're early. Still 20 minutes. Okay. Okay. Now choosing the number of groups based on the model selection. So this kind of models, these mixture models, have additional advantages, okay? And those additional advantages are what? It tells you even more things, okay? More information about the cluster, more information about the points. So two more extra things. The location of those ambiguous points, how we get the location of those ambiguous points from here, where their means are. If the mean is here or here or here, based on these we can then pinpoint its location. Okay? So here it's just giving you the clusters, okay? Just the clusters. We don't know those ambiguous points where they are. But in this case, we now also can pinpoint exactly where those points are, okay? So model-based classification gives you extra additional information, okay? And then those results for that points depends on the kind of model we are using, okay? So there are so many different types of model. Gaussian mixture models or any other distribution you take, okay? So it depends on the model, that shape will change, okay? So the covariance structure will change, the estimation procedure will change, okay? So to take home, these model-based clustering are influenced by the model assumptions. The model assumptions are those: are we using a Gaussian model? Are we using a model with this much mean, this much variance? And then the estimation method. Okay. Now it also fixes another problem for us. If you remember the k-mean algorithm, usually we use Euclidean type of distances. So our cluster is mainly a spherical cluster, okay? But when the shape of the data maybe is not completely spherical, then k-means has a problem. If we are in this case, we have a spherical cluster. We have a spherical cluster because the distances we are using here is kind of very close to Euclidean distance. And Euclidean distance works better when we have a spherical structure, cluster. But when we move from spherical clusters to something like this, to elliptical, then k-means cannot help us. So this is another benefit, advantage of using those model-based clustering. Okay? So basically this idea means that if we have, can you see from here? So if we have points like this, okay, and the points like this, so k-means works better with spheres. Maybe it will collect something like this, and then it's now trying to find the sphere, but it cannot find it. So problem. Okay, maybe it will say, okay, this one, but you missed these points. but now we have a Gaussian mixture model. You can take these points too. Okay, because it can make their way out. And why this is the case? Because k-mean just work with the cluster. They're roughly spherical, and it struggles when we have a correlated data. So in this case, this data is correlated. So that's why they're not now a sphere, but they're kind of moving like this. Okay, and k-mean struggles here. So then we have the Gaussian mixture models to also take correlated data into account. Now, who was asking the question? You. I don't remember your question, but I have some idea you asked me something. Let's see if it's answer your question. So, we have another method. We are tired, right? Yes.
Why so we can just use Mahalanobis distance to get the correlation and the eclipse instead of using equator distance, why we can fix the problem by using Mahalanobis distance?
But that will then not work good with k-mean. The way Euclidean distance is working, because Mahalanobis take into account correlations, and instead Euclidean don't care about the correlations between the points. It just says, okay, I need this radius, this diameter, for me this is enough. But Mahalanobis, okay, let me do something more for you. He's a bit additions, he wants to do something more. He explores the correlation. Okay? That's the only difference came to my mind. Because came Euclidean say, okay, this is the distance, for me this enough. I can just make for you clusters. That's it. But the other distance, it say, okay, let me do one step more for you. If there is some kind of correlation, I can also explore that.
But why do you say that the Mahalanobis distance doesn't work well with k-means? Does it mess with the centroid when they come closer?
Yeah, because then we cannot have like a perfect centroid, and we will move here and there. The problem. Did I answer your question?
Yeah, so basically what you're saying is that it messes with the approaching of the centroid, the iteration.
Yes, because then you don't have, if you are elongated this way, okay, maybe you can find somewhere, but if you are, I don't know,
Yeah, because it's about
somewhere
walking
like
the
this,
distance with the point.
yeah.
Okay, I can see.
Okay. So now this new method is kind of robust method, and which is called TCLUST, TC-LUST. It's robust and it handles outliers. It can handle outlier via trimming. Okay. So we have now added two more things to our portfolio. Two things. We added two new things. One is we can move from spherical cluster to elliptical cluster. True? The second thing we added to our portfolio, to our knowledge, is we can now deal with outliers. Okay? And the way to deal with those outliers is we trim them. We get rid of them. Okay, your outlier, you can leave. Okay, so the function to do this is T in MATLAB, T C last. You take these arguments. X is your matrix, K is the number of clusters you want a priori, alpha is how much percentage, how many points you want to trim. Okay,
So it is decided the outlier.
yes, in advance. And this guy controls the covariance, the shape of the cluster. Okay, just a quick example and then we can leave. So what does this alpha mean? This trimming variable means here. For instance, if we have alpha equal to 0.10 and we have n number of units equal to 100, so this means then out of 100 trim 10 points, 10 units. Okay, so 100 minus 10, then you will have just 90 points. So the rest of the 10 you excluded those are, yes.
Alpha 0, 10 is like the 0.5% of the smallest, 5% of the greatest.
Yeah, the two.
Like the triple mean.
Yes, the two extremes. So it takes into account the points which are too far. This is internal in this technique, in this method. Okay, so it prevents your data if you have those outliers to distort your data. So you trim them. Okay.
So how we can find the
We have to think. Is again the same situation. You hit and trial. Is a hit and trial method. Okay. So
Trimming is the only solution for these problems.
there are so many other solutions. The one we are dealing with is trimming. But it's an interesting topic for research. If you have an idea, we can try instead of trimming. So here, if we perform trimming, okay, then we have good 2 clusters. Okay, so the outliers now does not affect our clusters. Okay, we leave it here and see you tomorrow.